All right, folks, finishing off Chapter 4 here, the last section of Chapter 4, Section 4.9, we are going to take a look at antiderivatives. So up to this point in our calculus journey, we focused on finding derivatives. And differentiation, I'll be blunt, it's fairly straightforward. We're given a function. We have a plethora of rules to employ to determine its derivative. Very straightforward. Now, anti-differentiation, or doing an antiderivative, getting an antiderivative, I think that's kind of like a game, where we're given the answer and we have to come up with a question. Doing derivatives is like a game where we have a question and we give an answer. So far, in finding derivative, it's like a game. We have a question. What's the answer? So when we turn it around and do antiderivatives, it's going to be like a game where we're given the answer, and then we have to come up with the question. Oh, that word right there should say question. My apologies. We're coming up with the question. Folks, if someone gives you an answer and you have to come up with the question, that's a little bit more challenging. So for example, let's say someone says, hey, determine a function f of x, notice that's an uppercase f, whose derivative is f of x equals 2x. Now notice that's a lowercase f. Now I can come up with many functions that will work. Here's one. Big f of x equals x squared. We know the derivative of x squared is 2x. Here's another one. X squared plus 3. Because the derivative of x squared plus 3 is 2x. Here's another one. X squared minus 7. Because the derivative of x squared minus 7 is 2x. I've only listed 3 functions that would work here. There are an infinite number that would work. Each one of those 3 is called an antiderivative. And notice, each one of the 3, they just simply differ by a constant. So if I let C represent any real number constant, then f of x equals x squared plus c. That's how I would represent all of the antiderivatives. All infinite number of the antiderivatives can be represented by x squared plus c. And let me stress again, you heard me say it already here at the beginning of the slide. I know when I have a correct antiderivative. I just simply differentiate it. That's how I can check my work. So let's look at the following definition. We say a function, uppercase f, is an antiderivative of little f on an interval I if f prime of x, so the derivative of uppercase f, is equal to little f of x for all x that's in the interval. This theorem says that if uppercase f is an antiderivative of little f on an interval I, then all antiderivatives of little f on I has the form f of x plus c, where c is a constant. So here's the moral. I know the derivative with respect to x of x cubed is 3x squared. That means I can represent all antiderivatives of f of x equals 3x squared as x cubed plus c. Because when I differentiate x cubed plus c, I get 3x squared. Remember, the derivative of a constant is 0. Now, antiderivatives that we're seeing right now represent what is called a family of functions. And what I mean by that is for any constant c, x cubed plus c has a graph where each graph has the exact same shape and behavior and the exact same derivative. It's just shifted up or down depending upon the value of c. So let's do a quick example. Let's determine all antiderivatives for, well, there are 3 parts here. So folks, make sure you write these 3 parts down because I am heading off to the chalkboard to work through them. All right, folks, in this one we're supposed to determine antiderivatives for, and there were 3 parts here in A, B, and C. So the first one is the function f of x equals 4x cubed. So like I said, this is like a game. We have the answer. What was the question? What was the original function whose derivative is 4x cubed? I think it is x to the 4th plus c. And I know I am correct by differentiating what I think the answer is. And when I differentiate this, I get 4x cubed. So it checks. In part B, get the antiderivatives for f of x equals negative 8 over x to the 9th. Well, I'm going to rewrite this as negative 8x to the negative 9th. And then I think it's big F of x equals x to the negative 8th plus c. And again, I know if I'm correct by differentiating this. And does it give me negative 8 over x to the 9th? So if I differentiate it, derivative of x to the negative 8, well, that's negative 8x to the negative 9th. It checks. Part C. Part C, I want you to pause the video and I want you to do it real quick. And after you've done it, restart the video. I'll be here making sure you have it correct. All right, folks, let's see how you did in part C. What function has a derivative of cosine x? Hopefully you said it is sine x. Don't forget the plus c. And we know we're correct by differentiating sine x plus c. And that gives us cosine x. It checks. So let's head back to the slides and see what more we can do with antiderivatives. Okay, notice on that first example we did, all 3 parts, I stressed you know you have a correct answer by differentiating what you think the answer is. And it should have given you the original function, little f of x. Now, way back when we first started learning about differentiation, remember I introduced the notation d dx, square bracket f of x, and I said that it meant differentiate with respect to x, the function f of x. It was kind of shorthand for all those words. Similarly, I need shortcut notation to communicate all of the words, quote, determine an antiderivative for little f of x with respect to x. I don't want to keep writing all those words down. I don't want to say all those words. You don't want to keep writing them down. So the notation I'm going to introduce is called the indefinite integral, and it's given by this. So let's take it a step at a time. This thing here looks like an elongated S. It looks like someone took an S and kind of grabbed each end of it and stretched it out. That's called the integral sign. F of x, that's called the integrand. Dx, yeah, you remember dx, that's our differential, but dx is telling us the variable of integration. So when I read this, going forward, I'll just read it as the integral of f of x dx. And here's what it's communicating to you. It's communicating, hey, get an antiderivative for the function f of x with respect to x. Now, an indefinite integral is the same as an antiderivative. The process of getting an antiderivative, well, that process is called antidifferentiation, but it's also known as integration. So I'm probably going forward, I will rarely say anti-differentiation. I mean, it's a lot of syllables. Integration. So integration means the same thing as anti-differentiation. It is so important going forward for you to think that differentiation and integration are inverse operations. You know, just like addition and subtraction are inverse operations. Multiplication and division are inverse operations. You know, they undo each other. Differentiation and integration are inverse operations. Okay, now we need some rules. So some rules on, computing integrals, doing integration. The first one is going to be the power rule. And here's what the power rule says. It says when you integrate x to the n dx, or when you get the antiderivative of x to the n dx, that antiderivative is 1 over n plus 1 times x to the n plus 1 plus c, where n is equal to, or n cannot equal negative 1, because if n were negative 1, look, 1 over n plus 1 would be 1 over 0, and we just can't do that. So the power rule, it's kind of like the inverse operation of the power rule of derivatives. Remember, with derivatives, the n comes out front and you subtract 1 from the exponent. Well, here we're adding 1 to the exponent, and then in front, I like to say the 1 over n plus 1, that's the reciprocal of the new exponent. So that's how I use the power rule. And you'll see when we look at our first example, which is coming up right now. We're going to integrate the following. 3 parts here. So make sure you write all 3 of these down, because I'm heading off to the chalkboard to do them. And pay particular attention to how I do these. When I integrate, I get my new exponent first. Then out front, I will put the reciprocal of the new exponent. That's the 1 over n plus 1 part of the power rule. So let's head off to the chalkboard and work through these 3. All right, in this example, we were asked to integrate the following. Part A, integrate x to the 6th dx. So we have some new notation here. Keep in mind, this is the integral sign. It's telling you to get an antiderivative for x to the 6th with respect to x. And x to the 6th, remember, that has a name. It's called the integrand. So we know the power rule now. And I told you I would show you how I use the power rule. I get my new exponent first. So I get my new exponent by adding 1. So my new exponent is 7. And then out front, the little multiplier I put out front is the reciprocal of the new exponent. So the reciprocal of 7 is 1/7. And then I remember to tack on the plus c. And remember, you will know if you are correct by differentiating. You compute the derivative of this, and you better get the integrand. That's how you know you're correct. All right, part B. I would start off by writing it as 1 over x to the 5th. I would rewrite the integrand 1 over x to the 5th as x to the negative 5th. Now I use the power rule. The power rule says add 1 to the exponent. The little multiplier you put in front is the reciprocal of the new exponent. The reciprocal of negative 4 is negative 1/4. Don't forget to tack on the plus c. If you prefer to get rid of the negative exponent, you could write this as like this. These are equivalent answers. Part C. I want you to pause the video and I want you to do part C to see what you get. And then restart the video after you've done it, and I'll be here at the board working through it. All right, part C, I would start off by rewriting the integrand as x to the 1/2. Then I use the power rule. I add 1 to the exponent. Gives me a 3/2. The multiplier out front is the reciprocal of the new exponent. So it's a 2/3. Don't forget to tack on the plus c. And hopefully that's what you got. So let's head back to the slides and see what the next new rule is. All right, see, it's not so bad now that we have the power rule under control. This next theorem, well, it's the constant and also the sum difference rule. So for any constant, little c, when you integrate c times f of x dx, so you have a constant times a function, you can take that constant and rip it out front of the integral sign. And if you're integrating f of x plus or minus g of x, and there could be more than two functions in there, so when you integrate the sum or difference of two or more functions, you could split it up into integrating f of x dx plus or minus integrating g of x dx. So let's practice this stuff. So this example, well, we have three parts. Make sure you write each one of them down, because I am heading off to the chalkboard to work through all three parts. All right, so now that we've added to the power rule, we've added the, like a constant multiple rule. You can rip a constant out front, and the sum difference rule. Let's look at these three, parts A, B, and C in this example. In part A, I would start off by rewriting 5 over x squared as 5x to the negative second. And you know what, in part A, let me put in every possible step. Going forward, we probably won't be doing all of these steps. We'll be doing a lot of it mentally. So here's every possible step. I could rewrite this as integrating 5x to the negative second dx plus integrating a 4x squared dx. So that's using the sum difference rule. Here I could rip the 5 out front of the integral sign. And here I could rip the 4 out front of the integral sign. Okay, now I use the power rule, so I have a 5. And I'm going to leave a little space here for the reciprocal of my new exponent. So when I use the power rule, remember, I add 1 to the exponent. And then the reciprocal of the new exponent, well, the reciprocal of negative 1 is just negative 1. Plus 4. I leave a little space for the reciprocal of the new exponent. So when I use the power rule, I add 1 to get an exponent of 3. The reciprocal of 3 is 1/3. Don't forget to tack on a plus c. And then we could finish it off. We could write it. We know 5 times negative 1 is negative 5. So we could write it as negative 5x to the negative first, or negative 5 over x plus 4/3 x cubed plus c. All right, part B. Well, hey, my integrand, I could rewrite that integrand as a 12x to the 8th over x cubed minus x over x cubed. That looks like a good place to start, because now I can simplify 12x to the 8th divided by x cubed. When the bases are the same and you're dividing, subtract the exponents. So that gives me a 12x to the 5th. Here, the bases are the same, we're dividing, we subtract the exponents. So 1 minus 3 is negative 2. And I'm not going to write in all of these extra steps like I did in part A. I'm just going to verbalize them. I would integrate basically term by term. And when I integrate this first term, the 12, there's a 12 that's a multiplier there. So I need to remember the 12. Leave a little space. My new exponent, so see, I have to add 1 to this, so my new exponent is 6. Then in here I have to put the reciprocal of my new exponent, so that's 1/6, minus, okay, I add 1, and then out front I put the reciprocal of the new exponent, which is negative 1, don't forget the plus c, and then I would finally say, well, 12 times 1/6 is 2, so I have a 2x to the 6th minus a negative is plus. Or I could write it as 2x to the 6th plus 1 over x plus c. Okay, in part C, I'm going to do two steps at once. I'm going to start off by ripping the constant out front and then rewrite cube root of x as x to the 1/3. So now I can use the power rule. My new exponent, I add 1 to get 4/3. In here I put the reciprocal of the new exponent, which is 3/4. Don't forget the plus c. And let's see, 6 times 3/4, it's 18/4, it's 9/2. So 9/2 x to the 4/3 plus c. And one more time, we know each one of these would be correct by differentiating. And when we differentiate them, we should get the integrand. So here in section 4.9 exercises, I have a couple I'd like you to practice right now. So go to the section 4.9 exercises. Do numbers 24, 30, and 38. So pause the video, do these three in the section 4.9 exercises, and after you've done them, restart the video. I'll be here to make sure you're correct. All right, folks, at number 24, you were asked to integrate 3u to the negative second minus 4u squared plus 1 with respect to u. So I'm just going to do it term by term. I'm not writing in all those steps. So when I integrate 3u to the negative second, I have 3. Leave a little space. Use the power rule. So I add 1 to the exponent. Gives me a negative 1. The reciprocal of the new exponent comes in here. Well, the reciprocal of negative 1 is negative 1. Minus 4. Leave a little space. My new exponent, add 1. So that gives me a 3. The little multiplier in here is the reciprocal of the new exponent. And then the constant 1, well, the antiderivative of the constant 1 is just the u. And don't forget the plus c. And, you know, I suppose we could rewrite this as negative 3u to the negative first minus a 4/3 u cubed plus a u plus c. 30. Okay, I am going to begin by doing two things at once. I'm going to rip the 5 out front of the integral sign, and I'm going to rewrite that 4th root of x with a rational exponent. So I rip the 5 out front. The 4th root of x is x to the 1/4. Now I use the power rule. So I leave a little space. I add 1 to the exponent, so 1/4 plus 1 is 5/4. In here I put the reciprocal of the new exponent, so that's a 4/5. Don't forget the plus c. And then I clean this up. 5 times 4/5. Well, 5 times 4/5 is 4. And that's it for number 30. 38. Well, I'm going to have to do a little bit of work on that integrand. So when I look at the integrand, I look at the numerator, I say, well, hey, I can factor out a y. So I factor out a y. That leaves me with a y squared minus a 9y plus 20. And then I should be able to factor this y squared minus 9y plus 20. I think it factors to y minus 5 times y minus 4. And now we see a neat thing happens. The y minus 4's cancel out. So I'm left with integrating y times y minus 5 dy. And now I would distribute. So I can now do term by term integration. The antiderivative of y squared, that's 1/3 y cubed. The antiderivative of 5y, well, it's 5 times 1/2 y squared. That's 5/2 y squared. Don't forget the plus c. So hopefully you got those three. Let's head back to the slides and see what is next. All right, so hopefully that last example, the three parts made sense, and then the three exercises I asked you to do, hopefully you were able to do those no problem, and you got them correct. Moving on, folks, we get several integration quote formula. We get them for free. They cost us nothing. For example, we know the derivative with respect to x of sine x is cosine x. We know the derivative of sine is cosine. So for free, we know the antiderivative of cosine x dx is sine x plus c. That's why I keep stressing this differentiation and integration are inverse operations. You know a derivative, you get an integral problem for free. Now on page 277, there's a table, I think it's 4.9. It has the following formulas in it. I mean, you look at all these formulas. And it's like, when I was a student, I see a table or I see something in a box. It's like, that's important. I need to commit it to memory. But this table is telling you get stuff for free. These aren't formulas you have to commit to memory. Because you know the derivative of sine is cosine, for free, the integral of cosine x is sine x. That's all it's saying. You get this for free. Because you know the derivative of tangent is secant squared, for free, you get the integral of secant squared as tangent. So again, all of these formulas you get for free because you know certain derivatives. And because you know certain derivatives, coupled with the fact that differentiation and integration are inverse operations, it's free. So let's see. Let's start to continue this just a little bit further. All right, now we know the derivative of sine 4x is equal to 4 cosine 4x. We know that because, when you do the chain rule, derivative of sine 4x gives you cosine 4x times 4. So for free, we know the antiderivative or the integral of 4 cosine 4x dx is sine 4x plus c. We get that for free. So now, knowing that the integral of 4 cosine 4x dx equals sine 4x plus c, that allows us to determine just simply the integral of cosine 4x. It has to be a 1/4 sine 4x plus c. Notice where the 1/4 is coming from. I mean, if you were to differentiate sine 4x, you get the derivative to be cosine 4x times 4. But there's no 4 here. So you have to have this 1/4. So when you do the derivative here to check, that 1/4 times the 4 that would come from the chain rule, differentiating the 4x, we know the 1/4 times 4 is 1. So it's worth mentioning one more time. You can check to see if you have the correct antiderivative. You can just simply differentiate what you think the antiderivative is to see if you get the integrand. I mean, you've heard me mention this a lot now. I'm a firm believer in you can check your work, do the derivative. So let's look at an example. Going to have 3 parts here. A lot of trig ones here. This is going to be great. So folks, write these 3 down because I'm going to head off to the chalkboard to do them. And it looks like in part C, wow, that's going to be a fun one. So let's go to the chalkboard and let's work through these 3 examples. All right, this example, part A, going to integrate sine x minus cosine x dx. Just going to do it term by term. The antiderivative of sine is negative cosine x. The antiderivative of cosine is sine x. That is it. We are done. I would probably, until I get real comfortable with integrating sines and cosines, I would probably check this to make sure that I am correct. And remember, you check it by computing the derivative. So we know the derivative of cosine is negative sine. So opposite negative is positive sine. And the derivative of sine is cosine. So it checks. Part B, integrating cosine x minus cosine x over 4. Keep in mind that this cosine of x over 4 is really the same thing as cosine 1/4 x. So the antiderivative of cosine, well, that's sine. It's sine because the derivative of sine is cosine. And here we would have a sine, 1/4 x. Now keep in mind, if you were to differentiate the sine of 1/4 x, you'd get cosine of 1/4 x times 1/4, the chain rule. You'd have to differentiate the 1/4 x, which gives you a 1/4. There's no 1/4 in front of the cosine x. So I have to insert a little multiplier. So if I were to check this, I need to insert a multiplier that when multiplied by the 1/4, it would end up being neutralized. It would be a 1. I need to insert a 4. Don't forget the plus c. And I encourage you to check this. The derivative of sine is cosine. Check. Minus. When you differentiate this piece, it's 4 times cosine 1/4 x times 1/4. Chain rule. The derivative of 1/4 x is 1/4. And that 4 times 1/4 is 1. So this one checks. C. Okay, well, here's what I'm looking at. Here's what I see in C. That denominator, I'm looking at starting off with that denominator. It's a single term. So I'm looking at starting off by splitting the integrand into 2 fractions with that common denominator of cosine squared theta. So I'm looking at rewriting this as sine theta over cosine squared theta minus 1 over cosine squared theta. Okay, now I have a sine theta over cosine squared theta. So that's a sine theta over cosine theta. I'll write it down. It's a sine theta over cosine theta times a 1 over cosine theta. Well, we know sine over cosine is tangent. We know 1 over cosine is secant. So this is nothing more than secant theta tangent theta. And 1 over cosine squared is secant squared theta. So folks, the antiderivative of secant theta tangent theta. Which trig function has a derivative of secant tangent? That's right, secant. The antiderivative of secant squared theta. What trig function has a derivative of secant squared theta? That's right, tangent. And as I've been saying, and I said it on the slides, you get an awful lot for free because of knowing derivatives. Knowing the derivatives of trig functions, you get integral rules for free. You don't have to memorize them, you just know them. You get it for free. And all of this is predicated on the simple acknowledgement that differentiation and integration are inverse operations. They undo each other. So, I'm going to want you to practice a couple of these because it involves trig. So in the section 4-9 exercises, I'd like you to do numbers 42 and 48. So pause the video, go to the section 4-9 exercises, do number 42 and 48, and once you're done, restart the video. I'll be here at the board working through them. All right, here number 42, integrating sine t times the quantity 4 cosecant t minus cotangent t dt. I would begin by distributing that sine t. And the reason why is, remember, cosecant t is 1 over sine t. So when sine t gets distributed there, this simply just becomes a 4. Remember cotangent t, remember that's cosine t over sine t. So when sine t gets distributed there, it's like the sine t's cancel out and you're left with cosine t. Now it's just a matter of saying, well, the antiderivative of 4 with respect to t is 4t. The antiderivative of cosine is sine. Don't forget the plus c, and we're done. 48, I would have the exact same first step as 42. I'd look at the integrand and I'd say, you know what, I'm going to distribute that cosecant x. So I distribute the cosecant x. Antiderivative of cosecant x cotangent x. What is the antiderivative of cosecant x cotangent x? Well, we know the derivative of cosecant is negative cosecant cotangent. So that must mean that the antiderivative of cosecant cotangent is negative cosecant minus, okay, the antiderivative of cosecant squared. We know the derivative of cotangent squared is negative cosecant squared. So that means the antiderivative of cosecant squared must be a negative cotangent. Don't forget the plus c. And we're probably thinking a better way to write this instead of minus and negative is just using addition. All right, so hopefully you got both of those, 42 and 48. At this time we're gonna head back to the slides and see what the next topic is. All right, hopefully you're starting to feel a little better here about integration, and those 3 examples made sense, and you were able to quickly knock out the 2 exercises I asked you to do. We're going to conclude this section with a very, very brief look at differential equations. Now, I know most of you are going to end up taking a course because most of you are going to pursue some sort of engineering or maybe science degree. You're going to take a course dedicated to differential equations. In fact, the course is called Differential Equations. In general, a differential equation is nothing more than an equation that involves x, y, and some derivatives. As I just said, there's an entire course dedicated to differential equations. What we are about to do, this would probably be the first technique you would see the very first day in a differential equations course. It is a very basic method of solving differential equations called separation of variables. And I'm going to introduce some vocabulary here in this example. So in this example, we're going to find the general solution of the differential equation dy dx equals 2x minus 1, and the particular solution that satisfies the initial condition that f of 1 equals 1. So the general solution is going to produce like the family of functions, and the particular solution is we're going to identify out of that family of functions that one particular function that passes through the point 1, 1. So please write all this down because I'm heading off to the chalkboard to do it. All right, this is like a very, very basic, brief introduction to differential equations. We were asked to find the general solution of the differential equation dy dx equals 2x minus 1, and then the particular solution that satisfies the initial condition f of 1 equals 1. So when we find the general solution, we're going to end up with, like that plus c. It's that family of functions. There's an infinite number of functions because of the plus c on the end. That's the general solution. The particular solution will be determining the value of c that makes the graph of the function go through the point 1, 1. So I told you the method we were going to do, that I was going to introduce. It's called separation of variables. So let me write down the differential equation. Here's what separation of variables looks like. You want to get everything involving a y on one side of the equal sign and everything involving an x on the other side of the equal sign. So that would give us here dy equals 2x minus 1 dx. Next, we need to undo this differentiation. What undoes differentiation? That's right, integration. So we integrate both sides of the equation. Okay, over here on the left, the antiderivative of 1 dy is y plus some constant. I'll call it c sub 0. Over here on the right side, we do term by term, so the antiderivative of 2x is x squared. The antiderivative of 1 is x, plus there's a constant that I'll call c sub 1. Now I'm going to bring this constant over here and combine it with this constant to get y equals x squared minus x plus c. This is the general solution. It's the family of functions. I mean, if you fired up your calculator and you graphed x squared minus x plus, and you put in, like 6 different values of c, the shape of the graph's going to look the same for all of them. It's just shifted up or down. All of those graphs would have one thing in common, besides having the same shape. They all have the same derivative. Out of all of those graphs, we want to find that one that passes through the point 1, 1. And this was called the initial condition. So, f of 1 equals 1 implies, let me bring my general solution up here. We put 1 in for the y, 1 in for the x. Now we solve for c. So we get 1 equals 1 minus 1 is 0. Well, that didn't take too much to solve for c. We ended up with c being 1. Purely coincidental. We have all these 1s involved here. But that now tells us, once we know the value of c, we have the particular solution. We take this value of c and toss it into the general solution. So from this family of functions, this is the particular one that happens to pass through the point 1, 1. So, we'll just kind of practice this a little bit. In section 4.9, I'd like you to do number 62. And in number 62, it's really just asking you to come up with the particular solution. But you can't get the particular solution unless you first have the general solution. So pause the video, do number 62. When you're done, I'll be here at the board working through it. All right, here at 62, you were given g prime of x equals 7x to the 6th minus 4x cubed plus 12. And you were told g of 1 is equal to 24. And so we're coming up with the particular solution for g of x. Here, the book didn't give you this as dy dx. So you didn't have to worry about, doing a first step of algebra. But we do start off by integrating. I mean, in general, you're going to get g of x by integrating g prime of x. To undo the derivative, you have to integrate. So we have to integrate g prime of x, which means we have to integrate 7x to the 6th minus 4x cubed plus 12 with respect to x. I should put it, note that this is g of x. Term by term integration, the antiderivative of 7x to the 6th, that's going to be x to the 7th. The antiderivative of 4x cubed, well, that's just x to the 4th. The antiderivative of 12 is 12x. Tack on a plus c. So here's where we're at. This is our general solution. X to the 7th minus x to the 4th plus 12x plus c. So let me pull it over here. We know g of 1 is 24. So g of 1 is, put a 1 in for all the x's. And what has to come out is 24. Well, let's just do this. 1 to the 7th is 1. 1 to the 4th is 1. So we have 1 minus 1 plus 12 plus c equals 24. 12 plus c equals 24. C is equal to 12. Therefore, the particular solution. Now that we know what c is, we put it back into the general solution to get the particular solution, x to the 7th minus x to the 4th plus 12x plus 12. And that's all there is to this one. So let's head back to the slides and see what the next example is. All right, so we're seeing, in that basic differential equation and also the exercise I asked you to do, integration will undo the differentiation part. So let's let's look at another example. We're going to determine f of x given f double prime of x is sine x, f prime of 0 equals 1, and f of 0 equals 6. This is a pretty cool example, so write it down. And we're heading off to the chalkboard to work through it. All right, now let's check this one out. We're supposed to determine f of x. We're given f double prime of x is sine x. F prime of 0 is 1, and f of 0 equals 6. Well, we start off by trying to figure out what f prime of x is. So remember, differentiation and integration are inverse operations. So we can determine f prime of x by integrating f double prime of x. We'll undo to get to f prime. So, well, since f double prime is sine x, we need to come up with an antiderivative for sine x, which we know is negative cosine x. Don't forget the plus c. And so here's where we're at. F prime of x is equal to negative cosine x plus c. But since we are told f prime of 0 equals 1, well, we have f prime of 0 equals negative cosine 0 plus c. That has to equal 1. Cosine of 0 is 1. So we have negative 1 plus c equals 1. C is equal to 2. So at this point in time, we know the derivative, f prime of x, is negative cosine x plus 2. So to get f of x, we have to integrate f prime of x. To get f of x, we need to integrate f prime of x, which means we need to integrate negative cosine x plus 2. And here we get as an antiderivative negative sine x plus 2x plus c. So this is where we're at. And now we use the information, that we were told f of 0 equals 6. So f of 0 equals negative sine 0 plus 2 times 0 plus c, and that has to kick out a value of 6. So sine of 0 is 0. 2 times 0 is 0. So we have 0 plus c equals 6. C equals 6. So we have finally determined that f of x is negative sine x plus 2x plus 6. Pretty powerful stuff now that we've learned how to integrate. So let's head back to the slides and see what's next. Okay, as we saw in that last example, when you integrate f double prime of x, that gives you f prime of x. And then when you integrate f prime of x, that gives you f of x. And it wasn't too bad of an example. Now, I do have one final comment. And this comes from the basic physics stuff we've encountered in calculus. We know S of t generally represents a position function. We know v of t is the velocity function. And v of t is nothing more than the derivative of the position function. And then acceleration, that's the derivative of velocity, which means it's the second derivative of position. So if we're given an acceleration function, we can work backwards. We can determine v of t by integrating a of t. In other words, v of t equals the integral a of t dt. And then we can get s of t, the position function, by integrating v of t. So s of t equals the integral of v of t. So this kind of wraps up this final comment, kind of wraps up one more time, differentiation and integration are inverse operations. So we can integrate to undo the differentiation part. That's the beauty of an inverse operation. And on that note, there's nothing more for me to say about this section. So at this time, you can do all the exercises in section 4.9. So go do the exercises in section 4.9, and thanks for watching.